Welcome to the MySQL 8.0 DBA Prep course, where we begin our journey into mastering the 1z0-908 certification. In this initial chapter, we will explore the certification pathway and the core architectural pillars of the MySQL 8.0 ecosystem. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Oracle Corporation in any way. All trademarks, including MySQL and 1z0-1908, belong to their respective owners. Achieving the Oracle MySQL 8.0 Database Administrator certification is a significant milestone that validates your technical expertise in managing production-grade database environments. This course is meticulously designed to bridge the gap between theoretical knowledge and the practical, real-world skills required to pass the 1z0-908 exam. You will gain a comprehensive understanding of the MySQL architecture, covering critical topics such as the transactional data dictionary, the high-performance InnoDB engine, and advanced security configurations. The objective is to equip you with the proficiency needed to not only pass the exam, but to handle complex administrative roles with confidence and precision. By following this curriculum, you are investing in a structured roadmap that simplifies the transition from earlier versions like 5.7 to the modern, robust features of 8.0. The exam itself covers a broad spectrum of responsibilities, ranging from basic server management and configuration to the complexities of high availability and performance tuning. We will dissect the technical evolution of the server, paying particular attention to deprecated features that you must avoid in modern implementations. You will learn how to leverage the integrated MySQL shell and manage the transactional data dictionary, which significantly changes how metadata is handled compared to previous iterations. We will also dive deep into security protocols, including role-based access control and transparent data encryption, which are essential for maintaining a secure data environment. By the end of this course, you'll have a deep understanding of logical and physical backups, recovery strategies, and the performance optimization techniques that define a senior database administrator. Our approach focuses on the logic behind the technology, ensuring that you understand the why and not just the how of database administration. We will examine the exam structure, scoring mechanisms, and key performance areas that Oracle prioritizes in its current certification standard. As we navigate through the modules, you will become adept at interpreting official documentation and utilizing community resources to solve evolving database challenges. This foundation is crucial because the 1z0-908 exam requires you to demonstrate that you can effectively manage thread pooling, memory allocation, and the intricacies of InnoDB scalability. Let us begin this technical exploration by setting the stage for the deep dives that follow in the subsequent modules. See you in the next lecture. Welcome to our exploration of the InnoDB storage engine, where we will peel back the outer layers of MySQL to understand how data is actually managed and persisted. This chapter serves as the bedrock for mastering the inner workings of an enterprise-grade database system. If you are aiming to pass the 1z0-908 exam, you must move beyond simply executing queries to understanding how the database engine handles I/O and memory contention. We will examine the intricate design of the buffer pool, which acts as the primary cache for both table and index data, and how the least recently used algorithm manages page aging to maintain performance. We will also investigate the change buffer, which optimizes insertions by buffering changes to secondary index pages that are not currently in the buffer pool. Furthermore, we will demystify the adaptive hash index, a mechanism InnoDB uses to perform constant-time lookups for frequently accessed index pages, effectively bypassing the need for traversing the B-tree structure repeatedly. You will learn how the log buffer facilitates safe transactions by staging redo log entries before they are hardened to non-volatile storage. These structures are not merely academic concepts. They are the tools you must tune to ensure your production environments scale effectively under heavy load. Moving from memory to physical storage, InnoDB relies on a sophisticated hierarchy of tablespaces, extents, and pages to organize data on your disk. You need to grasp how the system tablespace houses the double write buffer and the undo logs, and differentiate between the traditional file per table structure and the more flexible general tablespaces. The transition from file-based metadata in earlier versions to the transactional data dictionary tables in MySQL 8.0 represents a significant leap in maintaining atomic, consistent information about your schema definitions. We will also dissect the redo log protocol, which implements a write-ahead logging strategy to ensure that data modifications are committed to the log before they are applied to the data pages. Understanding this lifecycle is critical because it explains why InnoDB can recover from a crash so gracefully by replaying these logs against the data files. This entire architecture is designed to balance the tension between performance and the strict ACID requirements that transactional databases demand. To ensure data integrity during a system failure, InnoDB utilizes the double write buffer, which prevents partial page writes that could lead to corruption. When a page is flushed from the buffer pool, it is first written to a contiguous area of the system table space before being written to its actual location in the data files. This architectural choice acts as a safety net, allowing the engine to restore a valid page copy from the double write buffer if a crash occurs during a write operation. We will also cover checkpointing, the process by which the engine determines which dirty pages in the buffer pool are safe to flush, thereby limiting the duration of crash recovery cycles. Finally, we will examine how undo logs support multi-version concurrency control by maintaining older versions of rows for transactions that need to see a stable snapshot of the data. By mastering these components, you gain the diagnostic capability to identify bottlenecks and address data reliability issues at the engine level. See you in the next lecture. Welcome back. We shall now explore the fundamental mechanics of how MySQL manages its internal memory footprint and client connections. By understanding these pillars, you can avoid the common pitfalls that lead to system instability and resource exhaustion. When considering memory allocation in MySQL, we must distinguish between global and session-specific memory pools. Global buffers are allocated once during server startup and are shared across all active threads, meaning their size essentially dictates the foundation of your server's memory usage. The most significant component here is the InnoDB buffer pool, which caches both data and indexes. Ideally, this occupies a substantial portion of your available system RAM to minimize physical disk I/O. We also have structures like the key cache, which is specifically relevant for MyISAM tables, though its prominence has declined in modern workloads. You should note that older features like the query cache were deprecated and subsequently removed in version 8.0 because they created massive lock contention points that hindered performance under concurrency. Effectively tuning these global structures requires a balancing act where you must leave enough overhead for both the operating system and session-specific requirements. Session-specific memory is allocated dynamically as clients connect and execute their individual SQL statements. Each session requires its own memory for various buffers, such as the join buffer, which holds data for join operations that cannot otherwise be optimized with indexes. Furthermore, the sort buffer facilitates sorting operations for complex queries, while read buffers are allocated to assist with table scans. Because these buffers are multiplied by the number of concurrent connections, spikes in traffic can lead to unexpected memory pressure. If you have 500 concurrent connections, suddenly increasing your sort buffer size by a few megabytes can result in multiple gigabytes of additional memory consumption. Monitoring these allocations is critical, and the performance schema memory instrumentation provides the granular visibility needed to track exactly where this memory is being consumed. The MySQL connection thread model serves as the mechanism for governing how these sessions are processed, defaulting to a one-thread per connection architecture. When a client connects, the server spawns a dedicated thread to handle the full lifecycle of that interaction, which is straightforward but can become expensive under high connection counts. To mitigate the overhead of frequently creating and destroying threads, MySQL maintains a thread cache defined by the thread cache size variable. By keeping idle threads in this cache, the server avoids the recurring cost of thread initialization, which significantly enhances scalability in high concurrency environments. For setups that require extreme connection counts, an alternative is the thread pool plugin, which decouples user sessions from individual threads and manages them through a more efficient scheduler. Choosing between these models usually depends on your specific application behavior and the distribution of your workload. Properly managing these memory limits is essential for maintaining server health and avoiding the dreaded killer. The or out-of-memory killer, is an operating system mechanism that terminates processes when it detects that the system is completely devoid of physical memory. If MySQL's internal buffers coupled with process overhead exceed available RAM, the kernel will aggressively reclaim memory, often by killing the MySQL daemon itself. To prevent this, you must base your configuration on real-world measurements taken during peak load periods rather than just theoretical guidelines. Ensure that you have accounted for the memory occupied by the operating system, file system caches, and any sidecar processes. Continuous monitoring through the Sys schema and performance schema tables allows you to refine these limits iteratively, ensuring stable performance without inviting unexpected crashes. I look forward to our next interaction, where we will continue expanding our knowledge of the MySQL server architecture. Welcome back. And in this section, we will cover the essential mechanics of installing MySQL 8.0 and managing its configuration files. This chapter provides the foundation for maintaining a performant and secure database environment. Determining the right deployment strategy starts with understanding the differences between Linux and Windows environments. On Linux distributions, you typically rely on package managers like apt or yum to handle binaries, which simplifies updates and dependency management significantly. Conversely, the Windows installer provides a graphical interface that packages the MySQL server as a Windows service, abstracting away some of the manual configuration required on Unix-like systems. Regardless of the operating system, the underlying binary structure remains remarkably consistent, though path conventions such as forward versus backward slashes can lead to occasional configuration friction if you're not careful. When you deploy in a Linux environment, you will inevitably interact with systemd, which serves as the core service manager for starting, stopping, and restarting the MySQL process. Proper integration with systemd ensures that the database service handles dependencies correctly, such as ensuring network interfaces are ready before the server attempts to bind to its port. By mastering these platform-specific deployment nuances, you ensure that your database instance is robustly provisioned from the very first moment it starts executing service commands. The primary configuration files, known as my.cnf on Linux or my.ini on Windows, act as the definitive source of truth for your MySQL instance's runtime behavior. MySQL enforces a specific search order when it initializes, typically beginning with system-wide settings, followed by directory-specific files, and ending with user-specific configurations in the home directory. Understanding this hierarchy is crucial because a configuration parameter defined later in the search order will override an earlier definition, which can lead to confusing behavior if you are unaware of how these files are layered. Within these files, you can utilize the include directive to pull in separate configuration files, which is an excellent practice for keeping your environment clean, modular, and maintainable. Imagine you have a main CNF file that handles generic paths, and you use an include statement to pull in a separate file specifically for InnoDB tuning parameters. This separation makes it vastly easier to manage settings across multiple instances or environments. If you ever find yourself struggling with a setting that simply refuses to take effect, trace the file loading order using the verbose help flag, which reveals exactly which files the server processed during its startup sequence. Always remember that the server only reads these files at startup, meaning changes to the file system require a restart unless you leverage more advanced dynamic configuration tools. While offline configuration files are standard, MySQL 8.0 introduced the set persist statement to modify configuration variables dynamically while ensuring they survive a server restart. If you execute a standard set global command, the change takes effect immediately in memory, but it vanishes the moment the MySQL service stops or crashes. By using the set persist keyword, however, the server writes the configuration change to a dedicated file named mysqldump.cnf, located in the data directory. Upon the next restart, the server reads this file automatically and applies the persisted settings before processing the final defaults in your standard configuration file. This approach is superior for high availability systems where you cannot afford long downtime, as it bridges the gap between ad hoc memory tuning and permanent configuration file updates. There's also a set persist only option, which is useful when you want to queue a configuration change that should only apply after the next restart, rather than altering the current memory state immediately. Using these commands wisely reduces the need for manual file editing and minimizes the risk of human error during configuration updates. Managing the initialization process requires a clear distinction between the initialize and initialize insecure flags used during the bootstrapping phase of a new data directory. When you run MySQL initialize, the server generates a random temporary root password and writes it to the error log, which forces you to reset it immediately upon your first login. This is the secure, production-ready path that adheres to the principle of least privilege from the very start of the installation lifecycle. In contrast, using the initialize insecure flag skips this password generation entirely, leaving the root account unprotected and potentially accessible to anyone who can connect to the server. While this may seem convenient for local development or automated testing pipelines, it introduces a significant security vulnerability that can easily be overlooked in a hectic production environment. Furthermore, the initialization process handles the structure of the data dictionary, which in MySQL 8.0 is a robust transactional repository for metadata that replaces the old MyISAM-based dictionary. Ensuring this initial setup is performed correctly is essential to avoid data corruption or metadata inconsistencies later in the server's lifecycle. Upgrading an existing MySQL installation requires a strategic decision between an in-place upgrade and a logical upgrade, each carrying different levels of risk and preparation. An in-place upgrade involves shutting down the server, replacing the binaries, and running the upgrade process on the existing data files, which is generally faster but more difficult to roll back if a critical issue arises. A logical upgrade, by contrast, involves exporting your data using tools like mysqldump or MySQL shell, and then importing it into a fresh, empty installation of the newer MySQL version. Although a logical upgrade is significantly more time-consuming for large databases, it offers the safest transition because the original instance remains untouched and fully functional during the entire process. Regardless of the chosen path, you are required to run the MySQL Upgrade Checker tool, which audits your instance for deprecated features, incompatible server variables, or legacy password plugins that will cause failures in version 8.0. Ignoring the findings of this checker tool is a common mistake that leads to severe downtime or broken applications following an upgrade cycle. Always perform these operations in a staging environment that mirrors your production data's complexity before attempting to bring a major version change into your live infrastructure. See you in the next lecture. Welcome back. In this section, we will systematically examine the server startup and shutdown lifecycle to ensure you understand how MySQL initializes its internal components and handles graceful exits. To understand the MySQL 8.0 startup sequence, we must view it as a deterministic progression of configuration loading and component initialization. When the MySQL binary executes, it first searches for options files in a predefined order, starting with the global /etc/my.cnf or /etc/my=my.cnf, moving to directory-specific files, and ending with command line arguments. Once these options are parsed, the server creates the initial memory structures and initializes the data dictionary, which in MySQL 8.0 is stored in transactional InnoDB tables rather than the legacy non-transactional metadata files. The server then moves to initialize the storage engine layer, primarily focusing on InnoDB, which must perform a critical recovery phase before the server accepts any connections. If the server was not shut down cleanly, InnoDB automatically reads the redo logs to roll forward committed transactions that were persisted to the log but not yet flushed to the data files, and rolls back incomplete changes. Only after this recovery process validates data integrity does the server bind to the network interfaces and initiate the thread pool or the individual connection listener threads. The error log is your primary diagnostic tool when the server fails to reach an operational state during this initialization phase. Often, startup errors stem from permission issues on the data directory, misconfigured system variables in the options file, or port conflicts where another process is already occupying the TCP port assigned to MySQL. If you find the server failing to start, look for specific messages indicating InnoDB buffer pool allocation failures or inability to open specific tablespace files. Misconfigurations in the data dictionary initialization are particularly sensitive, as corruption here can prevent the server from bootstrapping correctly. It is essential to understand that while the server might appear to start, it is not truly available until the network listeners are successfully opened and authenticated users are permitted to handshake. Monitor the tail of the error log during boot to distinguish between configuration errors and underlying file system corruption that may require manual intervention. When it comes to stopping the server, you have two primary mechanisms: sending a shutdown command via the SQL interface, or invoking a signal to the MySQL process from the operating system shell. A clean shutdown is always preferable because it allows the storage engines, specifically InnoDB, to flush dirty pages from the memory buffer pool to the on-disk data files. The InnoDB fast shutdown configuration variable dictates how much work the server performs during this exit sequence. If set to 0, the server performs a slow shutdown, which involves a full purge of the change buffer and a complete flush of the dirty pages, which minimizes the time required during the next startup event. If set to 1, which is the default, the server skips the full purge and flushing process, relying instead on the redo logs for consistency upon the next boot. Setting this to 2 performs a minimal shutdown, flushing only the logs and freezing the data files without waiting for the buffer pool flush, which is often used in emergency power loss simulation or rapid testing scenarios. The interaction between the binary log and the shutdown process is another critical area for a database administrator to master. During a graceful shutdown, MySQL ensures that all events stored in the binary log cache are flushed to the binary log files on disk, ensuring that no replication data is lost. This is vital for maintaining the consistency of downstream replicas that rely on the binary log for transaction playback. When you initiate a shutdown command, the server blocks new connections, waits for currently executing transactions to complete, and then proceeds to close the storage engines gracefully. If you instead use a SIGTERM signal from the operating system, the outcome is largely the same, but you lose the granular control afforded by the SQL commands. Always verify that your application layers have stopped sending transactions before triggering a manual shutdown to prevent potential transaction rollbacks. Understanding these mechanics is not merely an academic exercise. It defines your ability to recover from hardware failures or administrative mistakes. The distinction between a fast and a slow shutdown is a trade-off between how long you are willing to wait during the current shutdown versus how long you are willing to wait for the next startup. In production environments with extremely large datasets, a zero-mode shutdown can take a significant amount of time, sometimes hours, due to the heavy I/O required to flush everything. Therefore, most administrators stick with the default fast shutdown and rely on the robust recovery capabilities of the InnoDB engine to handle the state at startup. By mastering these parameters, you ensure that your database is always in a predictable state, regardless of whether you are performing a scheduled maintenance window or responding to an unexpected outage. I will see you in the next lecture. Welcome back. In this lesson, we will explore the nuances of managing MySQL Server variables, a critical skill for any database administrator aiming for the 1z0-908 certification. MySQL configuration variables act as the primary interface for tuning how the server behaves under load, managing security protocols, and controlling resource allocation. When we categorize these variables, we must first distinguish between their scope, which defines whether a setting applies to the entire server instance or only to the local connection. Global variables set the default state for the server and subsequent new connections, whereas session variables apply exclusively to the current client connection. This distinction is vital because changing a global variable does not automatically update existing sessions, nor does updating a session variable affect other users. You should think of global variables as the baseline configuration for the database engine itself. Conversely, think of session variables as temporary overrides that allow you to fine-tune performance for a specific, perhaps complex query operation. Mastering this distinction prevents the common frustration of changing a setting and not seeing the expected impact on your diagnostic data. Beyond scope, we must consider the mutability of variables, categorized as either dynamic or static. Dynamic variables can be altered while the MySQL server is running, giving you the flexibility to tune performance or authentication on the fly without interrupting service. Static variables, however, are immutable at runtime and require a modification to the configuration file followed by a full server restart to take effect. If you attempt to modify a static variable using the set command, the server will simply return an error, reminding you that deep-level architectural changes require a more deliberate approach. Knowing which category a setting falls into is essential for planning changes in production environments where uptime is measured against strict service level agreements. This knowledge prevents unnecessary downtime and helps you navigate the server's requirements with much higher precision and confidence. When it comes to actually implementation, the set statement provides the interface for modification, but its behavior changes based on the keywords used. The basic set command modifies the current session variable, while set global updates the global configuration for new connections. With MySQL 8.0, we gained the set persist and set persist only commands, which solve the long-standing issue of configuration drift across reboots. Set persist updates both the current global state and writes the new value to the mysqld auto.cnf file located in the data directory. The server reads this JSON formatted file during initialization, ensuring that your tuned values survive a restart automatically. Finally, set persist only is used for static variables, as it records the desired setting in the persistence file while acknowledging that the server must be restarted to apply the change to the active memory. To monitor these settings, we rely on the show variables command, which fetches data from the performance schema. Variables, tables, providing a live look at the current internal state of your server. Queries against performance schema are generally preferred in professional environments because they allow for sophisticated filtering and cross-referencing that basic show commands cannot easily replicate. For instance, querying the performance schema allows you to join variable settings with other thread-related metadata if you are trying to debug a specific connection's behavior. When you need to verify changes, especially after using persistent configuration, querying these tables ensures that the server recognized your input and applied the values as intended. Relying on these tables also helps you audit configuration changes, as the metadata stored within performance schema provides context on who initiated the change and when. Certain variables demand extra care because they define the foundational security and storage architecture of your server instance. The default authentication plugin, for example, dictates how incoming connections are validated, and changing this in a live production environment requires careful coordination with client-side drivers. Similarly, variables like mandatory storage engine allow administrators to enforce the use of InnoDB for all new tables, effectively blocking the creation of legacy storage engines that might not support modern security or reliability features. These variables act as architectural guardrails that prevent unauthorized or inefficient implementations within your database environment. When you set these via the persistent mechanism, you are creating a reliable configuration baseline that remains consistent regardless of how many times the server undergoes a maintenance reboot. Tracking configuration changes is a critical aspect of database administration, as it provides an audit trail for performance issues or security deviations. By leveraging the persistent configuration feature, MySQL maintains a record that identifies which variable was changed, by which account, and at what timestamp, keeping this metadata within the server's automated configuration files. This functionality removes the guesswork usually associated with troubleshooting non-standard behaviors that seem to appear out of nowhere after an unexpected service restart. Consistency is the hallmark of a stable database platform, and relying on these documented persistence tools is far safer than manual configuration file edits. Always prioritize these built-in management commands to ensure that your configuration remains synchronized across all nodes in a cluster. I will see you in the next lesson. Welcome back. Let's explore the architectural shift toward a transactional data dictionary in MySQL 8.0. In older versions of MySQL, metadata management was notoriously fragmented, relying on a collection of file-based artifacts scattered across the storage layer. You likely remember the struggle of managing FARM files for table definitions, .opt files for database-level configuration, and par files for partitioning schemes. These files were not transactional, meaning an unexpected server crash during a DDL operation could easily lead to metadata corruption or inconsistencies between the physical file state and the server's internal representation of the database schema. With MySQL 8.0, we have moved to a truly atomic transactional data dictionary stored internally within the InnoDB storage engine. This transition means that all metadata changes, such as modifying a table structure or altering a column, are now managed within the scope of consistent transactions. This fundamental change finally brings sanity to schema management by ensuring that the dictionary state is always synchronized with the actual data files on disk. By moving metadata into InnoDB, MySQL 8.0 introduces the concept of atomic DDL, which provides an essential layer of crash-safe consistency. Before this architectural update, if you executed a DDL statement that failed midway, you might be left with a partially modified file system and a database in an indeterminate state. Now, InnoDB ensures that DDL operations are atomic, meaning they either complete fully or roll back completely, preserving the integrity of the data dictionary. Because the dictionary is no longer reliant on external file operations, the server avoids the historical pitfalls of non-transactional file updates. This transition is not merely a back-end improvement, it is a prerequisite for more robust cloud-native deployments where reliability and predictable recovery are mandatory. When you perform an alter table operation, for instance, you can be certain that the metadata entry and the dictionary update are handled as a single unit, eliminating the risk of mismatched schemas after a restart. While the physical file system has become cleaner, you still need ways to query this metadata, which is where the information schema and the MySQL system schema come into play. The information schema remains your primary interface for gathering metadata about objects across the entire instance, providing a standardized, read-only view that applications and DBAs have relied upon for years. However, under the hood, these views now query the new system tables located in the MySQL database, which represent the actual persistent storage for the data dictionary. It is important to remember that these system tables are not intended for direct manual manipulation, as that could bypass the safety checks provided by the server engine. Instead, stick to standard DDL commands to change your schema and use the system metadata tables or views to monitor the current configuration. This separation of concerns allows the engine to optimize access to metadata while maintaining a clear, queryable interface for your administrative needs. Portability and recovery have also seen significant improvements due to the implementation of serialized dictionary information, or SDI. Every InnoDB tablespace now contains this metadata, which captures the table's essential structure in a serialized format that stays embedded within the tablespace file itself. This is a crucial feature for disaster recovery scenarios because it allows you to extract definition data even if the main data dictionary is unavailable, or if you're moving a tablespace between different server instances. You can use the IBD2SDI tool, a utility provided with the MySQL distribution, to inspect these tablespaces and pull out the JSON-formatted schema definitions without needing a running server. Being familiar with IBD2SDI is vital for modern DBAs, as it provides a path to verify the contents of IBD files when performing manual recovery or when moving tables physically between servers. By decoupling the metadata from the server-wide dictionary, MySQL creates a highly resilient system that supports advanced file management tasks safely. Finally, we must consider the implications for server upgrades and overall versioning, as this new architecture represents a distinct point of departure from older legacy systems. When migrating from older versions of MySQL to 8.0, the server must perform a substantial upgrade process to convert legacy metadata structures into the new transactional, InnoDB-based dictionary format. This is a one-way operation that cannot be reverted easily, so the upgrade process requires very careful planning and validation to ensure that all metadata is migrated without error. Versioning of the dictionary itself ensures that internal structures remain consistent as the server environment changes over time, preventing common bugs associated with older, file-based metadata caches. As a DBA, treat the transition to the new data dictionary as a critical milestone in your upgrade path, ensuring you have performed full backups before starting the migration process. Taking the time to understand these internal mechanics will make you significantly more effective when troubleshooting schema issues or managing complex deployment lifecycles. I will see you in the next lecture. Welcome back to our journey through the MySQL 8.0 architecture, where we will now focus on the critical task of observing and auditing your server via logging and status monitoring. In this chapter, we explore how to capture the internal state of your MySQL server through various logging mechanisms and real-time status indicators. An effective DBA cannot manage what they cannot observe. So understanding how to configure the error log, general query log, and slow query log is foundational for production stability. we will examine the structured JSON capabilities of the error log, which allows for easier integration with log aggregation tools, and discuss the nuances of capturing slow queries with microsecond precision. Beyond simple logging, we will dive into the binary log, the backbone of replication and point-in-time recovery. You will also learn how to leverage status variables to derive health metrics such as uptime and throughput. By the end of this module, you will be proficient in managing disk space used by logs and interpreting thread states to diagnose performance bottlenecks. The error log remains the most vital diagnostic tool in your arsenal, but in MySQL 8.0, its utility is greatly enhanced by structured logging. Instead of parsing unstructured text files, you can configure the server to output logs in JSON format, which provides a clean, machine-readable structure that modern monitoring pipelines can ingest without fragile regex patterns. When configuring these logs, consider the verbosity level, as captured by the log error verbosity variable, which dictates whether you are flooded with notes or only alerted to critical errors. Furthermore, the slow query log, when configured with the long query time set below 1 second, provides necessary insight into performance degradation using microsecond resolution. Pairing this with the general query log, which records every connection and statement, gives you a complete historical record of database activity, though one must be mindful of the significant I/O overhead that enabling the general log introduces in high-traffic environments. Managing disk space for these logs is a non-negotiable aspect of administrative responsibility, particularly regarding the binary log, which can rapidly consume storage if not governed by expiration policies. The expire log stays variable has been deprecated in favor of binlog expire log seconds, allowing for much finer control over how long binary logs persist before they are purged by the server. Configuring log rotation for the error log is also essential, often handled through external utilities or the built-in flush operations to ensure that a single log file does not grow to an unmanageable size. For auditability and compliance, these policies must be defined before deployment, as retroactive log management is rarely successful once disk partitions are exhausted. You should adopt a strategy where log retention aligns specifically with your backup retention window, ensuring that you always have the binary logs required to replay transactions against a physical or logical backup. Monitoring the server's current state revolves around the show status command and the underlying performance schema tables, which provide a snapshot of server health. Key variables like uptime illustrate the longevity of your current process, while connections and traffic metrics, measured in bytes sent and received, allow you to establish a baseline for normal operations. It is not enough to simply watch these numbers. You must correlate them with the thread states visible in the process list. When a thread is in a state of locked or sending data, you are looking at the symptoms of a deeper concurrency issue or an inefficiently indexed query. Identifying whether a bottleneck is caused by disk I/O, heavy sorting operations, or row-level contention is the difference between blindly restarting a service and surgically optimizing a slow-performing application. As you analyze thread states, look beyond the immediate duration and evaluate the specific lifecycle stage of the connection. A process stuck in sorting result often points to an excessive amount of memory being allocated for temporary tables, which may be hitting the disk rather than staying in RAM. When threads remain in waiting for table metadata lock, you are likely dealing with long-running DDL operations or uncommitted transactions that are holding up the rest of the application flow. By systematically checking these variables, you can spot trends in resource consumption before they manifest as outright service failures. Use the performance score schema tables as your primary data source for these insights, as the global status variables reflect a cumulative history that can sometimes hide short-lived intermittent spikes that cause significant user-facing latency. See you in the next lecture. Welcome to the chapter on Advanced Component Management, where we explore how modern MySQL extensibility works. We will specifically cover the transition from legacy plugins to the new component infrastructure. In the early days of MySQL, the architecture relied heavily on the plugin interface to extend functionality. Plugins are essentially dynamically loaded libraries that are linked into the server's process space. While effective, they have significant drawbacks because they depend on the server's global symbols and direct memory access. This tight coupling makes it difficult to manage complex dependencies or isolate potential failures. A plugin crash often results in the entire database server crashing, which is unacceptable for high availability systems. Furthermore, plugins lack a standardized way to communicate with each other, leading to an opaque and rigid ecosystem. As the complexity of database requirements grew, it became clear that a more robust architectural pattern was necessary. The MySQL 8.0 component infrastructure was designed to address these fundamental architectural limitations by introducing a service-oriented model. Unlike plugins, components are designed to be decoupled from the server's internal implementation details. They interact with the server and with each other strictly through service interfaces, which provides better abstraction and encapsulation. This means that a component does not need to know the internal data structures of another component to interact with it, provided the interface contract is respected. By leveraging this service registry, the server can manage dependencies more effectively and perform better isolation. This shift is essential for production environments where stability and predictability are paramount concerns for a database administrator. When we install features like the password validation component or the audit log, we are essentially extending the server's capabilities within this new framework. To install a component, you typically use the install component statement, which registers the component with the server and ensures that it is loaded correctly. Once installed, the information about these components is persisted in the mysql.component system table, ensuring that the state is maintained across server restarts. You can verify the list of currently installed components by querying the performance schema installed components table. This table provides visibility into which services are active, which is a crucial step when troubleshooting configuration issues or verifying compliance. If you need to remove a feature, the uninstall component command handles the teardown process gracefully. Managing system variables associated with these components requires an understanding of how they are scoped and exposed within the server. Components often export their own configuration parameters, which can be modified during runtime using standard set statements. However, because these variables are tied to the underlying component, you must ensure that the module is loaded before attempting to change its settings. If you attempt to modify a variable for a component that isn't active, the server will correctly report an error. It is also good practice to periodically review your system variable settings to ensure they align with your security policies. This lifecycle management is a vital part of your daily responsibilities when maintaining a stable production environment. Security is perhaps the most significant consideration when deciding to load external code into your database server. By nature, loading a plugin or a component allows that code to execute with the same privileges as the MySQL process itself. You must treat any third-party or custom component as trusted code, ensuring it originates from a verified source. Furthermore, you should analyze the interdependencies between components to minimize the attack surface of your installation. Excessive layering of components can create unexpected behaviors or performance bottlenecks that are difficult to debug under load. Always test these integrations in a staging environment that mirrors your production configuration before rolling out any new functionality to your primary database instances. See you in the next lecture. Welcome back. In this chapter, we will explore the mechanisms governing how you create, secure, and maintain user accounts within a MySQL 8.0 environment. Managing user accounts begins with understanding the user-at-host syntax, which is fundamental to how MySQL identifies an entry point for a connection. This notation creates a clear distinction between a user named APUser connecting from the local machine versus one connecting from a specific application server identified by an IP address. When you issue a create user statement, you are essentially defining both the identity and the allowed origin, which is our first line of defense against unauthorized network access. Authentication plugins bridge the gap between this identity and the security requirement of the server instance. By default, MySQL 8.0 employs the caching _SHA-2_password plugin, which provides significant improvements in security over the legacy MySQL native option password plugin. If you have older client applications that do not support SHA-256, you may find yourself forced to use the native plugin, but it is critical to understand the trade-offs involved in that decision. Always prioritize secure channels when utilizing older authentication methods to mitigate the risk of password interception during the handshake process. Once an account exists, administrative maintenance becomes a recurring task, particularly regarding account status and lifecycle management. The alter user command is your primary tool for operational control. most notably for locking and unlocking accounts when personnel changes or security anomalies occur. Beyond simple status toggles, modern MySQL administration requires proactive password management to reduce the surface area for credential-based attacks. You can configure password expiration policies globally or per account to force users to update their credentials at defined intervals. Furthermore, password history and reuse policies allow you to prevent users from cycling through a small set of known passwords, enforcing a higher standard of security hygiene. The introduction of support for dual passwords in MySQL 8.0 is a sophisticated feature designed to facilitate seamless credential rotation. By allowing an account to have both a primary and a secondary password, you can deploy new credentials across complex application clusters without causing downtime or immediate connection failures. Access control is logically separated into the definition of the identity and the assignment of privileges, which we manage through the grant and revoke commands. Privileges can be scoped globally, which applies to every database on the server, or restricted to specific schemas or even tables. A robust security design always follows the principle of least privilege, ensuring that an application service account holds only the permissions necessary for its intended data operations. For instance, granting create or drop privileges at a global level is rarely justifiable in a production environment where standard execution is the only requirement. If you find that permissions have been misallocated, revoke acts quickly to strip specific access rights without requiring the total destruction and recreation of the user account. This granular control allows for a flexible security model that adapts as the application architecture grows in complexity or scope during its deployment lifecycle. Resource management is the final component of a balanced account policy, specifically regarding the prevention of resource exhaustion by individual users. Even a legitimate user can unintentionally or maliciously initiate expensive queries that consume all available CPU or I/O bandwidth, potentially leading to denial of service conditions for other applications. We mitigate these risks by applying resource limits such as max queries per hour, max updates per hour, or max user connections directly to the user account metadata. When these limits are reached, the server rejects subsequent requests until the defined timeframe resets or the concurrency level drops. This defensive mechanism is an essential part of the database administrator's toolkit for maintaining consistent service availability. Implementing these caps might require some baseline traffic analysis first, as blindly setting them can lead to unexpected errors in high concurrency production environments. See you in the next lesson. Welcome back. In this chapter, we will explore how to manage database access efficiently through role-based access control, a cornerstone of secure MySQL operations. Managing privileges for individual users in a large environment quickly becomes an unmanageable task that is prone to human error. Instead of granting dozens of specific permissions to every developer or application service, we create roles that act as collections of privileges. When we define a role, we essentially create a template of access rights that can be applied to any number of users simultaneously. This approach allows us to align database security with real-world job functions rather than technical account names. If a professional changes departments, we simply revoke one role and grant another, ensuring that their access level is updated instantly. This reduction in administrative overhead also minimizes the risk of over-provisioning privileges, which is a common security failure. By centralizing our permission definitions, we make our authorization policy much easier to audit and replicate across different database instances. Creating a role involves the straightforward create role command, which behaves similarly to creating a user account, but acts strictly as a container for privileges. You grant privileges to this role using the standard grant statement, and you can even grant one role to another to build complex, hierarchical permission structures. When you link a user to a role, you use the grant command to associate that user account with the role you created. However, users do not automatically inherit the permissions of their assigned roles upon connection. A user must activate their roles within a session to exercise the granted privileges, which adds a layer of safety by preventing accidental misuse of elevated rights. We use the set role statement to switch between available roles or enable all roles assigned to the current user. This command empowers the user to choose the level of authorization necessary for their current task. If you want to ensure that specific roles are always enabled for certain users automatically, the mandatory role system variable proves indispensable. By defining a list of roles in this variable, the server will treat those roles as active for every user upon connection, regardless of their individual settings. This is particularly useful for global requirements, such as a base logging or monitoring role that every service account needs. For finer control over session-level stability, we utilize the Activate All Roles on login setting. When this variable is enabled, the server automatically enables all roles granted to a user when they authenticate, removing the need for an explicit set role command. This simplifies the experience for end users while maintaining a structured approach to permission management. It is a configuration choice that balances convenience with the intentionality of access control. Maintaining oversight of complex permission structures requires us to query the system metadata effectively. The information schema. Role Table Grants table provides a detailed map of which roles hold what rights, while the Enabled Roles view helps you identify which privileges a user possesses at any given moment. By inspecting these views, we can verify that the principle of least privilege is strictly enforced and that no user has cumulative access exceeding their technical requirements. Visualizing these hierarchies is essential because excessive nesting can lead to unintended privilege escalation paths that are difficult to debug. We should periodically perform a review of these assignments to ensure that they reflect the current security posture of our organization. Consistent monitoring of these metadata tables is the only way to guarantee that our administrative configuration remains intentional and secure. As our database architecture grows, leveraging these systematic views becomes the standard way to maintain transparency across the entire security stack and ensure our access policies are working as intended. I will see you in the next lecture. Welcome to this focused exploration of securing data in transit using transport layer security within our MySQL 8.0 environment. In this lesson, we will examine the technical mechanics of deploying encryption to protect sensitive data as it travels across your network. In the professional landscape, ensuring that data remains confidential while moving between a client and a database server is not merely a best practice but a fundamental requirement. Without TLS, traffic is transmitted in clear text, meaning any intermediary on the network can potentially intercept and read sensitive information. We address this by establishing an encrypted tunnel where the MySQL server proves its identity through a certificate, and the communication channel is subsequently locked down with cryptographic keys. When you configure MySQL for SSL, the server generates or utilizes existing certificate files to establish a handshake with the client. This handshake ensures that the communication is both authenticated and encrypted, preventing man-in-the-middle attacks that could otherwise compromise the integrity of your production environment. To facilitate this, the system uses digital certificates, which can be generated either through standard OpenSSL commands or the dedicated utility provided by MySQL, known as MySQL SSL Setup. This tool automatically creates the necessary CA certificate, server certificate, and server key, placing them in the data directory by default. When handling high-security production environments, however, you will often find that using a self-signed certificate, while functional, is less desirable than using one issued by a trusted certificate authority. If a certificate is lost or compromised, or if you simply need to enforce stricter security, managing a certificate revocation list becomes a standard operational task. This list acts as a registry of certificates that are no longer trusted, preventing attackers from using stale credentials to gain unauthorized access to the database service. Beyond simply enabling encryption, you have the granular power to mandate secure connections for specific database users as a matter of policy. By utilizing the Require SSL or Require X509 clauses when creating or altering a user account, you ensure that the server rejects any non-encrypted attempts from those specific identities. This is a powerful way to enforce a layered security strategy, where applications are restricted to only communicating over validated, encrypted channels. Consequently, if a developer attempts to connect using an insecure protocol, the database engine will terminate the connection immediately, effectively protecting the data from exposure. It is also important to consider the TLS version and the cipher suite, as these define the strength of the encryption and the protocols allowed for communication. MySQL 8.0 supports modern protocol versions like TLS v 1.2 and TLS v 1.3. and you should explicitly configure the server to prefer the highest possible standard available. You can control these settings through server variables, ensuring that older, weaker protocols are disabled to mitigate the risk of protocol downgrade attacks. Once your security policies are active, you must verify that they are functioning as expected by inspecting the server's telemetry. The Performance Schema library provides a dedicated table that tracks the status of encrypted connections in real time, allowing you to see exactly which connections are using which ciphers and versions. Monitoring this table regularly allows you to identify rogue connections or misconfigured clients that are falling back to unencrypted or low security states, enabling you to remediate issues before they become liabilities. Maintaining a secure database infrastructure requires this consistent rigor, ensuring that every layer of the transport stack is properly hardened against external threats. By combining these manual configuration steps with robust monitoring, you create a defensive posture that remains resilient regardless of the underlying network environment. Take these concepts and apply them systematically, beginning with a review of your current certificate lifecycle management. We have covered the essentials of TLS implementation, leaving you prepared to tighten your connection security in the next module. I will catch you in the next one. Welcome back, where we will explore the critical domain of transparent data encryption within MySQL 8.0 to secure your data at rest. This chapter covers the implementation and management of TDE to ensure compliance and robust security for your database infrastructure. Transparent data encryption, or TDE, serves as a fundamental security layer that protects your data at the storage level by encrypting physical files on disk. When you enable TDE, the InnoDB storage engine ensures that data pages are encrypted before they are written to the storage medium and decrypted as they are read into memory. This process is entirely transparent to the applications connecting to the database, meaning code changes are rarely required to implement this level of security. The mechanism relies on a two-tier key store architecture consisting of a primary master key and individual tablespace keys. The master key does not encrypt the data directly, but rather acts as a secure wrapper for the tablespace keys, which in turn perform the actual encryption of the data blocks. By separating these concerns, MySQL allows for efficient key management and provides a mechanism for frequent master key rotation without the need to re-encrypt every single data page on your disk. To facilitate this encryption architecture, you must configure a keyring component that handles the storage and retrieval of the master key. The most basic implementation utilizes the keyring file plugin, which stores the master key in a local server-side file, making it suitable for standard deployments where simplicity is prioritized. For more demanding enterprise environments, you should consider the keyring OKWE component, which interfaces with Oracle Key Vault to provide centralized and highly secure key management. Regardless of the chosen component, configuring these services requires modifying your configuration files to point to the correct plugin path and defining the necessary credentials. Once the keyring is initialized and active, the master key is created and stored, providing the foundation for encrypting your various tablespaces. It is imperative to remember that losing access to this keyring results in the permanent loss of all encrypted data, so you should treat your key management strategy with the highest level of professional care. The application of TDE in MySQL 8.0 is impressively granular, allowing you to secure specific parts of your database footprint according to your organizational security policy. You can choose to enable encryption for individual file per table tablespaces by using the encryption equals y clause within your alter tablespace or create table commands. Similarly, you can secure general tablespaces or even the entire system tablespace by applying these options during the creation or modification phase. When you issue an alter tablespace command, InnoDB performs the encryption process online, migrating data to the new encrypted state without preventing concurrent reads or writes. This flexibility allows you to selectively choose which sensitive data patterns require the highest tier of protection while preserving performance for less critical datasets. As you move forward, you should consistently audit your tablespace configurations to verify that encryption attributes are correctly assigned and maintained across your environment. Ensuring the longevity and security of your encryption infrastructure involves regular master key maintenance through the rotation process. Key rotation occurs when you issue the alter instance rotate InnoDB master key statement, which generates a new master key and rewraps the existing tablespace keys without requiring a full decryption and re-encryption of the underlying data files. This process is essential for compliance standards that mandate periodic credential changes to mitigate the risk of key compromise over extended periods. Because the rotation only impacts the master key and the wrapped tablespace keys, the operation is fast, atomic, and does not impose significant overhead on your ongoing database transactions. You should automate this rotation as part of your scheduled maintenance procedures to remain consistent with modern security best practices. Always ensure that your new master key is backed up correctly, as the older keys will eventually lose their relevance after the transition is finalized. While the performance impact of TDE is often overstated, you must consider the subtle costs associated with cryptographic operations on your CPU and memory. Encryption and decryption routines utilize the AES-NI instruction sets on modern processors, which significantly reduces the latency overhead introduced by the storage engine. However, you might observe a modest increase in CPU utilization, particularly in write-heavy workloads, as the system consumes cycles to process the encryption of dirty pages before they are flushed to the disk. Furthermore, because encrypted data does not compress as efficiently as plain text, you may notice that storage requirements for your backups are slightly higher if you leverage page-level compression in conjunction with TDE. When performing physical backups using tools like MySQL Enterprise Backup, the data remains encrypted within the backup files, which maintains your security boundary but requires that the backup environment also has access to the master key for restoration purposes. Full disk-level security requires that you also address logs, specifically the redo and undo logs, as they contain sensitive transactional data that could lead to information disclosure if accessed from the underlying file system. MySQL 8.0 allows you to extend your TDE policies to these binary and log streams, ensuring that your entire data path is hardened against unauthorized access. By enabling encryption for undo and redo logs, you prevent the exposure of row-level modifications that typically transiently persist on the disk during the lifecycle of a transaction. This configuration is particularly important for databases where sensitive information is frequently updated, as the log files map the state changes of these sensitive records over time. Implementing this comprehensive approach satisfies the most rigorous security audits and ensures that your data protection strategy is uniform across the entire storage layer. See you in our upcoming discussion regarding advanced security and audit logging plugins. Welcome back to our journey through the security landscape of MySQL 8.0, where we shift our focus to the implementation of the MySQL Enterprise Audit plugin to monitor user activity effectively. This chapter serves as a foundational guide for ensuring accountability within your database environments while meeting the strict demands of regulatory compliance. In any enterprise-grade database system, security is not merely about preventing unauthorized access, but also about observing and recording what happens inside the instance. The MySQL Enterprise Audit plugin provides a robust mechanism to track database activity, creating an immutable trail that is essential for satisfying auditors and maintaining internal governance. By leveraging this plugin, you gain visibility into connect and disconnect events, administrative commands, and specific data manipulation queries executed by users. The architecture of the plugin is designed to run asynchronously with the server process, ensuring that the impact on transaction latency is minimized even under heavy load. To begin using this functionality, you must first verify that the plugin is loaded in your server instance by checking the plugins table in the performance schema. Once active, the audit subsystem acts as a high-performance observer, capturing events as they occur and relaying them to the configured log output destination. Understanding that this plugin is a commercial offering part of the MySQL Enterprise Edition is vital for those studying for the certification, as these features are not present in the community version. It is an investment in observability that transforms an opaque database container into a transparent service where every significant interaction is formally logged. Configuring the plugin requires a structured approach to defining what exactly constitutes a notable event, as auditing every single query can quickly overwhelm your storage backend. You define this scope through the use of audit filters, which act as a firewall for your logging subsystem. These filters allow you to apply conditional logic based on specific criteria, such as user accounts, host IP addresses, or even targeted database namespaces. By carefully constructing these filters, you can effectively isolate high-risk administrative operations while ignoring the noise of frequent but benign application traffic. The system operates on rule sets, and you can modify these rules dynamically without needing to restart the database server, which provides the flexibility required for production hardening. A critical function in this workflow is Audit filter, which serves as the primary API for installing and managing these filtering policies. When you deploy these filters, the audit subsystem evaluates incoming events against your criteria to decide whether to record the action or discard it quietly. This capability is the difference between a useful log file and a useless wall of text that is impossible to index or analyze efficiently. Once your filtering logic is in place, you must turn your attention to the structure and lifecycle of the resulting log files, which are the artifacts that security teams will eventually consume. MySQL provides the flexibility to output these logs in either XML or JSON format, with JSON being the modern preference for integration with security information and event management systems. These machine-readable formats are essential because they facilitate automated parsing, allowing your log aggregators to flag suspicious activity in real time. For compliance frameworks like HIPAA, GDPR, or PCI DSS, the log file itself is not enough. You must also guarantee its integrity and availability over an extended period. This requires a solid strategy for log rotation and archiving to ensure that audit trails do not grow indefinitely and consume all available disk space. You should configure the server to rotate logs based on file size or time intervals, moving stale logs into a secure off-site storage location. Furthermore, implementing restricted file system permissions on these logs is a non-negotiable step to prevent attackers from masking their footprints after gaining unauthorized access to the database host. See you in the next lecture. Welcome back. In this chapter, we explore advanced authentication and external security mechanisms to harden your MySQL 8.0 environment. Centralized identity management is a frequent requirement in enterprise environments where maintaining local user accounts becomes an administrative burden. MySQL 8.0 addresses this by supporting integration with existing infrastructures such as LDAP, Kerberos, and PAM. These external authentication plugins allow the server to delegate the verification of credentials to a trusted domain controller or identity provider, instead of checking a local password hash. When you enable LDAP or Kerberos, the MySQL server no longer manages the user's primary credentials, which effectively synchronizes account lifecycle management across your entire organization. This reduces the risk of orphaned accounts remaining active within the database after an employee has been offboarded from the company's central directory. Configuring these components involves not only enabling the relevant plugin on the server, but also ensuring the client environment is properly prepared to provide the required authentication tokens. It represents a shift from siloed security to a unified, manageable framework that inherently scales better as your infrastructure grows in complexity. A powerful auxiliary mechanism for managing these external identities is the use of proxy users. This feature allows you to map an external user authenticated via one of the external plugins to an internal MySQL account that possesses the necessary privileges. By using the proxy privilege, a specific internal user serves as a template or a functional role that the authenticated external identity adopts upon connection. This abstraction layer is quite useful because it decoupling the identity that exists in your LDAP or Kerberos store from the granular permissions required to interact with schema objects. You can define a single internal proxy user with limited scope and allow multiple external identities to map to it, streamlining the grant management process significantly. Ultimately, this approach minimizes the number of records you need to maintain within the MySQL system schema while enforcing strict access control policies through the mapped internal account. Even with robust external authentication, the database remains a prime target for automated brute force attacks aimed at discovering passwords for existing accounts. The connection control plugin provides a necessary defense by introducing an artificial delay to the server's response after a series of failed authentication attempts. You configure this by setting the number of allowed consecutive failures and defining the baseline delay that increases as more failures occur. This does not strictly prevent access, but it renders brute force operations computationally impractical for an attacker trying to guess passwords at scale. When the threshold is reached, the server forces the client to wait before resuming communication, effectively throttling the rate at which guesses can be processed. It is important to monitor the status variables exposed by this plugin to identify legitimate users who may be accidentally tripping these security thresholds. Finally, we must consider the integrity of the MySQL system schema, which serves as the foundation for MySQL security. This schema stores the user table and other critical credential metadata that define who can connect and what they can execute. You must treat access to this system schema with the same level of care as you treat your most sensitive production customer data. Granting broad select or update permissions on tables within the MySQL schema is a severe security misconfiguration that can lead to elevation of privilege attacks. Always audit the accounts that possess administrative roles and ensure that the principle of least privilege is applied to system objects. By safeguarding the MySQL.user table and its related structures, you ensure that the authentication architecture itself remains tamper-proof, which is the cornerstone of any reliable database security policy. Until the next lecture. Welcome back. In this session, we will examine the mechanisms required to secure the network edge and communication channels of your MySQL 8.0 instances. To control server accessibility at the network layer, we primarily rely on the bind address and port directives located within our configuration files. By default, MySQL often binds to all available network interfaces, which exposes the service to any addressable host on the network. Setting the bind address to 127.0.1 restricts connections to the local machine, while specifying a particular internal IP address limits access to a known private network segment. This effectively hides the server from the broader untrusted environment, serving as a primary defense in depth measure. Furthermore, changing the default port from 3306 to a non-standard port can act as a minor deterrent against automated port scanners searching for default service installations. While security by obscurity is never a primary control, reducing the surface area by limiting where the server listens is a fundamental requirement for a hardened production environment. Always ensure that these configurations align with your infrastructure's physical or logical network segmentation. Another critical vector for security is the local in-file configuration variable, which dictates whether clients can use the load data local in-file command. While this feature is convenient for importing bulk data, it introduces a significant risk of file injection attacks if an attacker gains control over a client application or environment. When enabled, a malicious server could potentially read files from the client file system that the user has permissions to access, simply by requesting them during the data loading process. Therefore, the secure, best practice approach is to disable this global capability by setting local in-file to 0. By establishing a policy where this variable is strictly forbidden, we eliminate this specific class of client-server side-channel attack. If bulk loading is required, it is far safer to move files to the server's secure local file system and perform a standard, non-local import operation. Beyond basic network and file constraints, MySQL Enterprise Edition offers the Enterprise Firewall, which provides a sophisticated layer of protection against SQL injection and unauthorized query patterns. This component functions by intercepting incoming queries and comparing them against a pre-approved whitelist of SQL patterns or profiles. You essentially put the firewall into a learning mode, where it logs the legitimate DML activity of your production applications over a representative timeframe. Once the traffic profile is stable, you switch it to enforcement mode, where the server will reject any query that does not conform to the established whitelist. This effectively neutralizes SQL injection attempts, as an attacker's dynamically generated malicious payloads will inevitably deviate from the validated patterns. Integrating this feature ensures that only known, trusted request structures ever reach the InnoDB storage engine for execution. Managing administrative access during high-traffic surges is a persistent challenge for database administrators, as standard connections may become queued or exhausted under heavy load. MySQL addresses this through the dedicated administrative interface, which uses a separate port, typically 33062, to allow connections when the main socket is overwhelmed. This specialized interface is designed expressly for administrative tasks, ensuring that if you need to perform emergency repairs or kill stalling processes, you can still gain access to the server. Because this port does not share the same connection threading restrictions as the main listener, it provides a consistent, reliable path for authorized personnel. It is crucial to restrict access to this administrative port using network-level firewalls to ensure that only trusted management hosts can utilize this critical access path during stress events. Keeping this pathway clear is often the difference between a minor performance bottleneck and a full-scale managed service outage. Finally, we must consider the performance and security trade-offs involved in the skip name resolve setting. When this option is disabled, the server performs a reverse DNS lookup on the connecting client's IP address to ensure that the host name matches the host-based account privileges defined in the user table. While this adds a layer of validation, every new connection handshake is subjected to the latency of a DNS lookup, which can significantly slow down application startup times. By enabling skip name resolve, we force the server to avoid these lookups, relying exclusively on IP addresses for authentication checks. This not only yields a measurable performance improvement for connection-heavy workloads, but also removes a reliance on an external, potentially compromised DNS infrastructure. From a security standpoint, as long as your environment uses static internal IP addresses and firewall zones, disabling reverse DNS lookups is a sound architectural choice that hardens the connection flow. I hope this overview helps you understand the intersection of network configuration and service security. See you in the next session. Welcome to this chapter on data masking and anonymization, where we will explore how to protect sensitive information within your MySQL environment. We will cover the practical implementation of masking techniques and how to leverage specific functions to secure PII. In an era where data privacy is paramount, storing sensitive information such as personally identifiable information, or PII, requires a robust strategy that extends beyond mere encryption at rest. While transparent data encryption handles the physical layer of your storage, it does nothing to prevent an authenticated user from querying that raw data and viewing sensitive content in clear text. This is where data masking comes into play, serving as a secondary layer of defense that hides sensitive values from unauthorized eyes while maintaining the structure of the database. Effectively implementing this requires a shift in how we think about access control, moving from a binary notion of having access to a data table to a more nuanced view of what exactly that access entails. By utilizing the MySQL Enterprise Data Masking and De-identification component, we can intercept queries and transform data on the fly before it reaches the end user. This allows developers and analysts to perform their tasks without ever coming into contact with authentic, sensitive identifiers, effectively neutralizing the risk of data leakage caused by insiders or compromised application accounts. To begin working with these capabilities, you must first ensure that the masking component is properly installed as a server plugin. Once active, the component provides a suite of functions that allow for both static and dynamic masking of your data. Dynamic masking is particularly useful because it does not alter the underlying data stored on the disk. Instead, it modifies the result set at runtime based on the privileges of the user executing the query. You might use the mask inner function, which replaces characters within a string with a fixed value, such as replacing the middle digits of a credit card number with asterisks, while leaving the outer digits intact for identification purposes. Conversely, mask outer is often employed when you need to hide the majority of the data, only showing a small portion, such as the final 4 digits of a phone number. These functions are remarkably efficient, and because they operate at the SQL layer, they integrate seamlessly into your existing query patterns without requiring a complete refactoring of your application logic. Another essential aspect of this toolkit is the generation of synthetic, yet realistic data, which is facilitated by functions like genRange and genBlock. When you need to provide a dataset to developers for testing purposes, you cannot simply provide raw data, as that would constitute a violation of privacy regulations. Instead, you can use these generation functions to replace real values with statistically plausible but entirely fake data points that maintain the correct data type and format. For instance, if you are masking an age field, it is important that the generated value still reflects a valid integer range. Otherwise, your application logic might fail or trigger invalid arithmetic operations. This is where data type integrity becomes critical, as the goal is to make the masked data look and feel as close to the original as possible while being entirely delinked from the actual individuals in your system. By using these functions within view definitions, you can expose a sanitized version of your database to non-privileged users, ensuring they can work with the interface while the underlying PII remains safely masked. As you build these masking strategies, you must remain vigilant regarding the risk of statistical inference. which can inadvertently lead to de-anonymization. Even when individual fields are masked, if the dataset is sufficiently large or cross-referenced, the combination of multiple masked or partially revealed values can often identify a unique individual. Imagine a scenario where you mask a name but leave a birth date, zip code, and gender unmasked. The intersection of these three data points is often enough to identify a specific person with a high degree of certainty. Consequently, managing your masking dictionary is not just about choosing which functions to apply, but about understanding the granularity of the information you are exposing. You should document the impact of your masking policies and periodically audit your views to ensure that the cumulative information does not reconstruct the sensitive attributes you aim to protect. It is also wise to test your masking implementation against various query patterns to identify any holes where raw sensitive data might still be leaking through, whether via direct access or derived statistical insights. See you in the next lecture. Welcome back to the course, where we now turn our attention to the critical domain of data durability and disaster recovery. In this chapter, we will systematically break down the methodologies required to secure your database against system failures and data loss. Effective database administration requires us to move beyond simply running backup commands and instead think in terms of service-level agreements. The core of this discipline rests on two metrics: recovery time, objective, or RTO, and recovery point objective, or RPO. RTO represents the maximum tolerable duration that your database can be offline following a disaster before the impact becomes unacceptable to the business. Conversely, RPO defines the maximum tolerable age of the files that must be recovered from backup storage for normal operations to resume. Establishing these two targets is not a technical exercise, but a business negotiation that dictates your entire infrastructure strategy. If you aim for an RPO of 0, you are effectively pursuing a synchronous replication or zero-loss configuration, which carries significant performance overhead. If you accept an RPO of 1 hour, you gain simpler, less intrusive backup options, but you accept that some amount of data generated in that window is permanently lost upon a failure. Without clear definitions for RTO and RPO, you have no objective basis to choose a backup strategy, as you cannot measure whether your current approach actually meets organizational needs. When we choose a mechanism to capture data, we are generally deciding between logical and physical backups. Logical backups, such as those produced by utilities like mysqldump or mysql export the data as a series of SQL statements that can recreate the database structure and content. These files are human-readable, portable across different MySQL versions or storage engines, and allow for granular restoration of specific tables or databases. However, they are fundamentally slow to produce, and even slower to restore because the database must parse the SQL and reinsert every row, which involves significant storage engine overhead. Physical backups, by contrast, involve copying the underlying data files, such as the IBD files in InnoDB, directly from the file system. This approach is highly efficient for large datasets because it is essentially a binary copy that bypasses the SQL layer entirely during restoration. While physical backups are generally faster and capture the state of the system exactly as it resides on disk, they may require more care regarding consistency and are often less flexible when you only need to recover a single table from a huge database. The state of the database during a capture process introduces the distinction between cold, warm, and hot backups. A cold backup requires the database server to be completely shut down, ensuring that no data is being modified while the files are copied, which provides the highest level of consistency but imposes absolute downtime. A warm backup generally refers to a state where the server is running, but the database is locked or read-only, preventing writes during the procedure. In modern production environments, we almost exclusively rely on hot backups, where the server continues to handle reads and writes while the backup utility captures the data. To achieve this, tools like MySQL Enterprise Backup use techniques such as taking a snapshot of the log sequence number or utilizing undo logs to reconcile changes that occurred during the copy process. Choosing between these states is essentially a trade-off between the complexity of your toolchain and the amount of interference you are willing to tolerate in your production environment. Your choice of backup frequency and coverage is typically categorized as full, incremental, or differential. A full backup captures every piece of data in the target, providing a clear and comprehensive recovery point. but it is rarely feasible to perform this daily in large-scale environments due to storage costs and I/O duration. Incremental backups capture only the data that has changed since the last backup of any type, which makes them extremely storage efficient and fast to run. The trade-off here is that restoration requires starting with a full backup and then replaying every subsequent incremental file, which can make the recovery process quite tedious and prone to failure if one of the links in that chain is corrupted. Differential backups fill the middle ground by capturing all changes since the last full backup, meaning you only need the latest full backup and the latest differential to perform a restore. Each organization must map their storage constraints and latency requirements to these patterns to ensure that the recovery process remains reliable and within the defined RTO. Developing a disaster recovery plan is the culmination of these technical decisions, and it must account for factors beyond the backup files themselves. You must consider the total database size and the bandwidth required to transfer those backup files to an offsite location, as local backup is useless if the entire data center is compromised. Storage constraints also dictate retention policies, forcing a balance between how long you keep historical data and the cost of the secondary storage medium. Another subtle factor is the granularity of recovery, which forces you to decide if you need the ability to restore a specific table, facilitated better by logical backups, or if a full database restore is sufficient. Granularity and speed are often at odds, and a well-architected DR plan acknowledges that you might need a multi-tiered strategy. This often looks like physical backups for rapid base restoration combined with logical backups of critical tables for surgical interventions. I will see you in the next session. Welcome to this chapter on logical backups, where we will examine how to effectively utilize MySQLDump and MySQL Pump to safeguard your data. We will move beyond basic syntax to understand the transactional implications of these tools in production environments. When we talk about logical backups, we are essentially referring to the process of exporting your database metadata and data into a set of SQL statements that can be replayed to recreate the schema and information. This approach is highly portable, making it an excellent choice for small to medium-sized databases that do not require the raw speed of physical backups. The primary tool for this task, MySQLDump, generates a plain text file that is readable and modifiable, which can be an advantage when you need to selectively restore objects or perform migrations across different operating systems. However, because it relies on reconstructing data through SQL commands, it is inherently slower than copying binary table files directly, and this overhead increases significantly as your dataset grows into the multi-terabyte range. Understanding when to favor this method over physical alternatives requires a nuanced view of your recovery point objectives and the specific performance characteristics of your storage engine. The command line syntax for MySQLDump is quite expressive, allowing for granular control over exactly what gets exported from the server. To capture everything, you would provide the All Databases flag, while targeting a single schema is as simple as defining the database name followed by specific table names, if further isolation is required. To ensure your dump includes essential procedural code, you must explicitly include the routines and triggers flags, as these objects are not exported by default. Furthermore, if you are working within a replication environment, the setGTD-purged flag is critical because it captures the global transaction identifier state exactly where the dump occurred. Without this state, orchestrating a point-in-time recovery or setting up a new member in a replication cluster becomes significantly more difficult, as the server will not necessarily know its position in the binary log sequence relative to the dump data. Perhaps the most important flag for anyone working with the InnoDB storage engine is single transaction, which is essential for ensuring consistency without disrupting ongoing operations. When you initiate a dump with this option, the client issues a start transaction statement before retrieving data, which provides a consistent snapshot of the InnoDB tables as they existed at that exact moment. Because InnoDB supports multi-version concurrency control, other sessions can continue writing to the database while the dump process reads the requested data without the need for shared or exclusive locks. This is a massive improvement over traditional locking mechanisms that would otherwise render your database effectively read-only during the entire duration of the backup process. You should almost always use this flag when dealing with transactional tables. Otherwise, the dump will resort to table-level locking, which is usually unacceptable in a live environment. We must also consider the role of MySQL which serves as a more modern, parallelized successor to the classic mysqldump utility. The key architectural difference here is the use of multiple threads to process data, which allows for significantly faster export speeds on systems with adequate CPU and I/O resources. Instead of processing databases sequentially, MySQL can split the workload across multiple connections, which is particularly beneficial when you have a high number of schemas or large tables. It also features more sophisticated object filtering, allowing you to exclude specific database components or data subsets with greater precision than was historically possible. While it replaces much of the functionality of MySQLdump, it is important to note that the output can sometimes differ slightly in structure, and it is not a direct API replacement in every automated script you might have already deployed. Accelerating the restore process is just as important as the backup itself, especially when you are racing against a recovery time objective. Because logical backups are just collections of SQL statements, the server must parse, compile, and execute every single insert operation during a recovery, which can be extremely slow. To mitigate this, you can disable foreign key checks and unique checks during the restore to prevent secondary validation overhead, which can cut down import times by a substantial margin. You should also consider increasing the buffer pool size temporarily if you are performing a bulk import, or alternatively, tuning the redo log configuration to handle high insertion volumes without triggering constant disk flushing. By managing these parameters strategically, you can transform what would have been a day-long restore into a process that fits comfortably within your maintenance windows. I will see you in the next lecture. Welcome back. Let's explore the mechanism of physical backups and the capabilities offered by MySQL Enterprise Backup. This chapter focuses on high-performance backup strategies that allow us to maintain database availability during the data protection process. When we transition from logical backups like mysqldump to physical backups, we are essentially shifting our strategy from exporting SQL statements to copying the actual raw data files that reside on the disk. MySQL Enterprise Backup, commonly referred to as MEB, provides a robust solution for this by performing non-blocking backups of InnoDB tables, while the server remains fully operational and responsive to incoming queries. Unlike logical backups, which must parse and reconstruct data, physical backups are much faster to restore because they involve file-level operations that bypass the overhead of SQL parsing and execution. The MEB engine achieves this by tracking changes to the data files while the copy process is running, ensuring that the resulting snapshot is consistent with a specific point in time. This is particularly crucial for large datasets where the duration of a logical dump would be prohibitive, potentially impacting production performance significantly. Mastering this tool is a prerequisite for any DBA managing enterprise-grade databases, as it provides the foundation for reliable disaster recovery and data migration workflows. At the core of MEB usage are the backup to image and copyback commands, which serve as the primary methods for data ingestion and restoration. The backup to image command aggregates the database files, logs, and essential metadata into a single, compressed stream, which can then be saved directly to local storage or pushed to cloud repositories like Amazon S3 or Azure Blob Storage. This integration simplifies infrastructure management, allowing us to offload backups from local disk pressure to durable, scalable cloud-based environments. Once an archive is created, the copyback operation allows us to restore those files back to the database directory structure, effectively rolling the state of the database to the point when the backup was finished. During this restore process, MEB automatically handles the metadata synchronization, ensuring that the data dictionary remains coherent with the restored files. It is important to note that physical backups captured by MEB also include the necessary binary logs to facilitate point-in-time recovery after the restore operation concludes. The consistency of a physical backup depends on how closely the tool tracks the transactional state of the InnoDB storage engine. MEB works by reading the data pages directly from the files while simultaneously monitoring the redo log to capture any modifications occurring during the backup duration. By applying the redo logs during the restore process, the database reaches a transactionally consistent state that mirrors the exact moment the backup completed. To ensure that our backups are not corrupted during the transfer or due to storage issues, MEB includes a validate command that checks the integrity of the backup image. This command scans the contents of the backup and verifies headers and checksums to catch hardware errors before we find ourselves in a desperate restoration scenario. While there are community alternatives like Percona Extra Backup, which also provide non-blocking snapshots for InnoDB, MEB is specifically engineered and supported for the Oracle MySQL ecosystem. Choosing between these often comes down to the support requirements of your organization and the specific features needed for cloud integration or advanced enterprise security settings. See you in the next session. Welcome back. In this lesson, we will focus on the mechanics of point-in-time recovery, commonly referred to as PITR, which allows us to restore a database to a specific second before a catastrophic event occurred. Recovery is not merely about restoring a static snapshot of your data. It is about bridging the gap between that snapshot and the exact moment of failure. When we perform a physical or logical backup, we are capturing a point in time, but the database continues to evolve the very next millisecond. The binary log is the critical component here, as it records every data modification transaction as an event. If we lose data at 10 a.m., but our last full backup was at 2 a.m., the binary log contains the definitive audit of every change made in those intervening 8 hours. PITR is essentially the process of replaying this log against the restored backup. However, simply dumping the log is rarely sufficient because we must isolate the specific moment where the corruption or accidental deletion took place. This requires a surgical approach to the binary log, ensuring that we stop precisely before the irreversible error occurred. To execute this recovery effectively, we rely on the MySQL binlog utility, which acts as the interpreter for our binary log files. You can pinpoint the recovery window either by a specific human-readable timestamp, such as October 27, 2023, 9:59 and 59 seconds, or by using GTID coordinates if your server has global transaction identifiers enabled. Using GTIDs is generally safer and more precise, as they track the transaction across the entire replication topology rather than relying on the server's local clock, which can sometimes introduce ambiguity. When you extract these events, you often find yourself dealing with massive files that contain changes from multiple databases. The MySQL binlog utility provides the Anonymization option, which acts as a filter to ensure you are only replaying transactions relevant to your target schema. This is not just a convenience, it is a sanity check to prevent the accidental overwriting of data in unrelated databases that might have been receiving traffic concurrently. Once you have identified the range and filtered your events, the replaying phase begins by applying these statements to the restored baseline data. This process is effectively a manual synchronization of state, and it carries its own set of unique risks, particularly regarding data integrity. If the binary log was not flushed to disk immediately upon commit, you might experience data loss because the binary log events were held in the OS cache and subsequently lost in a crash. This is precisely why the sync binlog variable, ideally set to 1 for maximum durability, is a fundamental configuration requirement for any production environment tasked with PITR. By forcing a disk sync for every binary log commit, you ensure that the log is truly a source of truth that you can rely on when the worst-case scenario unfolds. Without this configuration, the ledger of your transactions has holes, and a complete recovery becomes a mathematical impossibility. During the replay phase, you may occasionally encounter conflicts, especially if you're attempting to replay transactions into an environment that already contains partial or conflicting data. It is vital to understand that the replay is essentially a sequential execution of the recorded SQL statements. If the database engine encounters a primary key conflict or a missing record that existed in the source state but not in the restored baseline, the process will halt. Resolving these discrepancies involves carefully inspecting the binary log content and potentially editing the output file before applying it. You are effectively performing a form of surgery on your transaction stream, removing the erroneous events while keeping the preceding and following legitimate modifications. This level of manual intervention is why I stress that monitoring your binary log growth and health should be a regular, proactive task, rather than a reactive one during an emergency. In practice, the complexity of PITR scales with the volume of traffic your server handles daily. When extracting segments of the log, always favor the smallest viable window that encompasses the incident. This limits the blast radius of any mistakes made during the replay, and simplifies the process of validating the state of the data once the restoration is complete. Always verify the state of your indices and constraints after applying the binary log, because replaying DDL and DML operations sequentially can occasionally expose edge cases that were handled differently when the original transactions were executed. If you have been diligent with your backups and your sync bin log settings, the process becomes a predictable operation rather than a desperate measure. You now have the fundamental knowledge required to navigate the recovery window and reconstruct your database after a failure. I will see you in the next lecture. Welcome back as we turn our attention to one of the most critical aspects of database performance: query indexing and optimization. In this session, we will demystify how the database engine navigates your data and explore the tools available in MySQL 8.0 to ensure your queries remain performant as your datasets grow. To understand indexing, we must first look at the B-tree structure, which serves as the default storage mechanism for InnoDB tables. A B-tree is inherently balanced, meaning the path from the root node to any leaf node is always equal, ensuring predictable lookups. When you query a table, the optimizer traverses the tree, comparing values until it reaches the leaf level where the actual row data or a primary key pointer resides. While B-trees excel at range scans and equality lookups, hash indexes offer a different trade-off by mapping key values directly to data pointers. Hash indexes are incredibly fast for equality comparisons in memory, but do not support range operations, making them impractical for sorting or inequality filtering. In MySQL 8.0, the B tree remains the workhorse for most relational workloads, providing the depth control and concurrency required for transactional integrity. Optimizing indexes requires moving beyond basic single-column structures into the realm of composite and functional indexes. A composite index allows you to organize data by multiple columns, but you must adhere to the leftmost prefix rule for it to be effective. If your index spans columns A, B, and C, the optimizer can utilize the index for queries filtering on A, and B, or all three, but not on B or C alone. MySQL 8.0 introduced functional indexes, which allow you to index the result of a function or expression rather than the raw column data. For instance, if you frequently query by the year derived from a timestamp, creating an index on that expression prevents the engine from performing full table scans. Furthermore, descending indexes allow the engine to satisfy sort requirements without an additional sorting step in the execution plan, which significantly reduces CPU overhead when pulling result sets. Testing changes in a production environment is notoriously high risk, which is precisely why invisible indexes exist. An index marked as invisible is maintained by the background processes, keeping it up to date with data changes, but the query optimizer treats it as if it does not exist. This allows you to toggle an index off to measure its impact on performance without the time-consuming process of dropping or rebuilding it. If an index is unused over a long duration, it becomes a liability because it consumes disk space and degrades write performance during inserts and updates. Regularly identifying and pruning redundant indexes is essential, as the optimizer spends time evaluating each one before deciding on an execution plan. Every index must justify its own existence by providing a measurable improvement in read velocity that outweighs the cost of maintenance. For specialized data requirements, we must discuss spatial and full-text indexes. Spatial indexes, utilizing R-trees, allow for efficient geometric data retrieval, which is critical for GIS applications where proximity searching is the primary access pattern. Full-text indexes, conversely, operate on an inverted index architecture to track tokens appearing across large text fields, enabling sophisticated searching that traditional B-trees simply cannot handle. However, utilizing these tools requires a clear understanding of how cardinality, the ratio of unique values to total rows, affects the cost-based optimizer. The optimizer uses statistics gathered through index sampling to decide if an index is selective enough to warrant usage. If statistics become stale, the optimizer may make poor decisions, leading to inefficient full table scans even when a well-structured index exists. I look forward to seeing you in our next session. Welcome back. Today, we are going to unpack the mechanics of query diagnostics by analyzing execution plans in MySQL 8.0. When we interact with a relational database, we define our intent through SQL, but the database engine determines the actual physical path to retrieve that data. The explain command acts as a window into the optimizer's decision-making process, showing us how the engine intends to access tables. If you prefix a select statement with explain, MySQL returns a structured row indicating the scan type, the anticipated number of rows processed, and whether indices are utilized. A const join type, for instance, represents the best-case scenario where the optimizer identifies a single record during the initial planning phase, usually within a primary key or unique index lookup. On the other end of the spectrum, an all scan signals a full table scan, which often indicates that the engine could not find a suitable index or that the dataset is so small that a full survey of the blocks is perceived as more efficient than traversing a B-tree structure. Understanding these classifications is fundamentally about grasping the cost implication of each operation, as each step carries a weight that directly impacts the latency of your application. Beyond the basic operation types, the extra column inside the explain output provides crucial context that often points to specific performance bottlenecks. When you see using index, the engine is performing an index-only scan, meaning it gathers all required columns directly from the B-tree leaf nodes without traversing the base table records. While this is highly desirable, seeing using file sort might suggest that the engine needs to perform an additional pass to order the result set because the current indexing strategy does not support the required sort order. Similarly, using temporary indicates that the optimizer requires a temporary table to process the query, which can be computationally expensive if the dataset size forces the spill of that temporary structure to the disk. By interpreting these indicators, you can refactor your queries or adjust your indexing to favor more efficient paths that rely on memory-resident operations rather than expensive disk I/O. For deeper diagnostics, the explain analyze command takes this further by providing the actual execution statistics, including the actual elapsed time and row counts, compared to the original estimates. When textual output feels insufficient for complex multi-table joins or deep recursions, you can leverage the JSON format to visualize the optimizer's internal hierarchy. By using format equals JSON, you receive a structured representation that demonstrates the nesting of operations, providing a much clearer picture of how the engine handles subqueries and join dependencies. This format allows you to see the calculated cost for each operator, helping you identify which part of a complex query is adding the most overhead. If the execution plan still seems illogical, the optimizer trace is your next line of defense, as it logs the internal evaluation steps the optimizer followed before choosing the final plan. This trace reveals discarded alternative paths and the reasons why they were rejected, such as high cost estimates or index ineligibility. Investigating this trace often clarifies why a specific query is not behaving as expected, turning an educated guess about performance into a data-driven diagnosis. In practice, identifying bottlenecks requires a systematic approach of observing the plan, analyzing the join efficiency, and validating the cost estimates against actual data distributions. A query might start with an index range scan that seems correct at first glance, but if the optimizer overestimates the number of matching rows, it might choose a nested loop join that becomes inefficient as the table size grows. You must look for mismatches between the rows examined and the rows returned, as these discrepancies frequently signal that the statistics held in the data dictionary are outdated or misleading for the engine. Frequent execution of analyzed table helps keep these statistics fresh, ensuring the optimizer has a realistic map of the data distribution before deciding on the execution path. As you iterate on your queries, always remember that an execution plan is not static. It is a snapshot of the engine's best effort based on current information, and your role is to ensure that information leads to the most performant outcome. See you in the next lecture. Welcome back. This chapter focuses on mastering the performance schema and the Sys schema for real-time diagnostics and performance tuning in MySQL 8.0. When we approach the challenge of optimizing a database, we often fly blind if we rely solely on standard status commands. The performance schema serves as the instrument cluster of your MySQL server, providing a low-overhead telemetry framework that captures granular details about server internals. It is essentially a storage engine that collects data at runtime, designed specifically for monitoring. By default, it is enabled, but the depth of data depends on the configuration of instruments and consumers. Instruments represent the events or aspects of the server you wish to track, such as specific mutexes, file I/O operations, or memory allocations. Consumers represent the tables where this information is stored and preserved for later analysis, such as the events, weights, summary, global, by, event name table. To use this effectively, you must understand that enabling every single instrument carries a measurable performance cost. We must be surgical in our approach, enabling only what is necessary to diagnose the current latency or contention issue. To configure the monitoring environment, you interact with the Setup Instruments and Setup Consumers tables located within the Performance Schema database. Updating the enabled column in these tables allows you to toggle data collection for specific event categories instantly, without requiring a server restart. If you are investigating a disk I/O bottleneck, you would target the stage/IO//SQL instruments to gain visibility into file access delays. Once these are enabled, the database engine begins populating the associated event tables, which act as rolling buffers of historical activity. It is useful to remember that these tables often use a memory-only storage engine, meaning they reset upon server restart unless you explicitly export the data. This transitory nature reminds us that the performance schema is for immediate introspection, not for permanent historical auditing of every transaction that has ever occurred. By observing wait events, you can pinpoint exactly which thread is blocked and precisely what resource it is waiting for, be it a row lock, a table metadata lock, or a physical file read. Navigating raw performance schema tables can feel like reading assembly code when what you really need is a high-level summary. This is where the Sys schema becomes indispensable, as it provides a collection of views and stored procedures that aggregate performance schema data into human-readable insights. Instead of manually joining complex tables to find the most resource-intensive queries, you can query simple views like statement analysis or memory global by current bytes. These views abstract away the internal complexity, allowing you to quickly identify your top slow queries or the sessions consuming the most memory. Essentially, the Sys schema transforms technical data bits into actionable information that a database administrator can use for daily health checks. Whether you are using MySQL Workbench or the MySQL shell, these tools often tap into these Sys views to present visually intuitive reports on latency or lock contention. In troubleshooting, start by examining the table I/O statistics to observe how frequently your indexes are being scanned versus updated. High latency in file I/O frequently leads back to inefficient query patterns or inadequate buffer pool configurations. By tracking the wait events related to synchronous versus asynchronous reads, you can understand if your database is being throttled by the underlying storage hardware. Lock contention is another area where the Sys schema shines, as it provides views like InnoDB walk waits to quickly reveal which transactions are queuing behind a held record lock. If you fail to resolve lock contention, throughput will inevitably collapse regardless of how well-tuned your indexes are. By iterating through these metrics regularly, you establish a baseline for your server's normal behavior, which makes identifying anomalies significantly easier when performance inevitably dips under load. The data provided by these schemas is only as good as the questions we ask of it during our routine maintenance. Focus your efforts on the highest latency events that directly impact user experiences, rather than getting lost in optimization for the sake of optimization. Identifying memory consumers helps you tune the configuration variables we discussed earlier, ensuring that thread buffers and file descriptors are sized appropriately for your workload. Always verify that your monitoring configuration does not introduce its own new bottleneck on the server by enabling too many granular instruments at once. A disciplined approach to utilizing these schemas will provide you with the evidence needed to justify hardware upgrades or schema refactoring to your stakeholders. Precision and observation are the foundations of effective database administration. I will see you in the next lecture. Welcome back. Today, we are diving into the core aspects of InnoDB performance tuning to ensure your database operations remain efficient under heavy demand. We will examine critical configuration parameters and architectural strategies for optimizing your storage engine throughput. The InnoDB buffer pool is arguably the most significant memory structure for database performance, acting as the primary cache for both data and index pages. When sizing this pool, a general rule of thumb for dedicated database servers is to allocate roughly 70 to 80% of total system memory. For extremely large datasets that exceed physical memory, partitioning the pool into multiple instances via the InnoDB GB buffer pool instances parameter helps reduce lock contention across multi-threaded workloads. Each instance manages its own free lists and LRU lists, effectively allowing the engine to scale better when multiple threads access pages simultaneously. To mitigate the cold start problem where queries remain slow until the cache is populated, you can leverage buffer pool dumping and loading. By enabling InnoDB buffer pool dumping shutdown and InnoDB buffer pool load at startup, the engine persists the page metadata to disk, allowing it to pre-warm the cache upon a server restart. This mechanism significantly reduces the latency spikes typically associated with transitioning from a warm state to a cold state after maintenance. Managing write throughput requires careful balance, particularly when configuring the transaction log and I/O capacity settings. The InnoDB log file size variable defines the size of each log file group, which directly impacts the frequency of checkpointing activity. Larger log files permit more sustained write operations before the engine must flush dirty pages to disk, though they also increase recovery time following a crash. You must pair this with InnoDPII capacity, which dictates the number of I/O operations the server can perform per second when writing dirty pages. If your hardware is SSD-based, you should set this value significantly higher than the default to avoid stalling write threads during background flushing tasks. The flushing behavior itself is governed by adaptive flushing, which dynamically adjusts the rate at which dirty pages are written based on the velocity of log generation. This keeps the redo log space usage predictable and prevents the server from experiencing periodic hang cycles caused by massive, abrupt flush operations. In highly concurrent environments, the InnoDB thread concurrency setting becomes a lever for preventing CPU thrashing. While setting this to 0 theoretically disables concurrency control, leaving it to the engine to allow as many threads as possible, high-traffic systems often benefit from explicit tuning. If the thread count is too high, context switching overhead degrades performance. Yet if it is too low, you prevent the database from fully utilizing available hardware resources. Furthermore, the resource groups feature in MySQL 8.0 allows for a more surgical approach to scheduling. By creating resource groups, you can bind specific user sessions to particular CPU cores, which is invaluable for isolating intensive ad hoc reporting queries from the critical background tasks that sustain the database. This prevents your analytical workloads from starving the essential purge threads or cleaner threads that are tasked with maintaining consistency and reclaiming fragmented space. Managing the purge thread effectively is the final piece of the throughput puzzle in long-running OLTP applications. The purge thread performs the necessary cleanup of old row versions that are no longer accessible to any active transaction, a process essential for MVCC garbage collection. When undue log growth is outpacing the purge process, you risk performance degradation and increased I/O pressure as the engine struggles to scan through bloated version chains. Monitoring the history list length through status metrics will tell you if the purge thread is falling behind and requires additional throughput capacity. By ensuring that your configuration aligns with your hardware capabilities and workload patterns, you maintain a predictable environment where the storage engine operates smoothly. Consistency in your tuning approach rather than reactive micromanagement is how you achieve sustainable database performance in a demanding 8.0 environment. See you in the next lecture. Welcome back to this series on the MySQL 8.0 ecosystem. In this session, we will explore the fundamental mechanics of replication and the varied formats available to facilitate data synchronization across servers. At its core, MySQL replication operates on the principle of a primary server pushing changes to one or more replica servers to ensure data redundancy and load distribution. When a client performs a write operation on the primary, the server records that event into the binary log, which acts as the source of truth for all downstream updates. A dedicated dump thread on the primary reads these binary log events and streams them to the I/O thread running on the replica server. This I/O thread then writes the incoming data into a relay log, a local file that serves as a staging area for subsequent execution. Finally, the SQL thread on the replica reads the relay log entries and applies the contained modifications to the local database, effectively mirroring the state of the primary. This asynchronous process is the foundation upon which features like read scaling, geographic distribution, and analytics offloading are built in professional environments. Understanding the replication formats is critical because they dictate exactly how your data modifications are captured and interpreted by your replica servers. Statement-based replication, or SBR, logs the actual SQL statements executed on the primary, such as an update or a delete command. While this format is generally compact, it can introduce non-deterministic behavior if, for instance, a statement relies on functions like UED or RAND, which might return different results on the replica. Conversely, row-based replication, or RBR, records the specific changes made to individual rows rather than the SQL text itself. This approach is highly robust and deterministic, ensuring that replicas remain in perfect synchronization with the primary regardless of environmental factors, although it often results in much larger binary logs. The mixed format provides a flexible middle ground by defaulting to SBR, but automatically switching to RBR whenever a statement involves non-deterministic logic or potentially unsafe operations. Configuration of data flow is handled through specific server variables that allow for granular control over what information is transmitted to slave servers. Filters like replicate do DB and replicate ignore DB are classic mechanisms used to filter binary log events, allowing administrators to choose specific databases for replication while excluding others. While these options are still present, they should be applied with caution if you're working with cross-database queries or foreign keys. A common pitfall is the expectation that these filters will always provide security through obscurity, whereas they are intended strictly for managing replication topology. When designing your architecture, always evaluate if your workload requires complete datasets on replicas, or if targeted filtering is a genuine requirement for your specific business logic. Mastery of these components ensures that your high-availability solutions are not only performant, but also surgically accurate in their distribution of database traffic. See you in the next lecture. Welcome back. Today we are starting our exploration of global transaction identifiers, a critical component for modern MySQL high availability. We will examine how this mechanism replaces traditional file-based replication coordinates to create a more robust topology. In older MySQL replication setups, we relied heavily on binary log file names and byte offsets to track the position of a replica in relation to the source. This approach feels fragile today because any minor structural change or manual intervention could easily lead to an invalid position. With global transaction identifiers, or GTIDs, we identify each transaction uniquely across the entire replication topology. A GTID is composed of a source, UUID, and a sequence number, combined as a single string. This structure ensures that a transaction, once committed on the source, maintains its identity as it propagates to every replica. Because the identifier is global, we no longer need to track where a file ends or begins to establish a recovery point safely. This shift fundamentally changes how we think about replication stream alignment. To implement this, you must configure the server parameters GTIDO mode and enforce GTIDOAT consistency, which work in tandem to ensure reliable operation. Setting GTIDO mode to on requires that all transactions are GTID logged, while enforce GTIDOAT consistency prevents the execution of operations that cannot be safely logged using GTIDs. You will find that these settings are not dynamic on older versions, though MySQL 8.0 allows for an online transition if done carefully. When enabled, the server updates binary logs with the unique identifier for every transaction committed. These identifiers are stored in the gtdi.executed variable, which represents the set of all transactions that have been applied. By tracking this set internally, the server can automatically determine the missing transactions needed by a replica. This auto-positioning capability removes the manual labor traditionally required during replica promotion. The structural advantages of this model become apparent when you face a failure in your primary node. In a traditional environment, you would manually calculate the correct binary log coordinates to point the new replica at the appropriate source. With GTIDs, The replica simply asks the source for all transactions not contained within its local GT-IQ executed set. This mechanism makes failovers nearly instantaneous and significantly reduces the probability of human error during intense recovery procedures. Furthermore, GTIDs make point-in-time recovery much cleaner, as you can target exact transaction ranges rather than guessing coordinates in a multi-gigabyte log file. While the complexity of the global state might initially seem higher, it actually simplifies the overall operational mental model. Managing the persistent state of these identifiers involves understanding both the GTID executed and GTID purged system variables. The GTID executed variable tracks all globally finished transactions, while the GTID purged variable identifies transactions that have been removed from the binary logs to save disk space. When you are performing backups, it is vital to capture these variables correctly to maintain the consistency of the entire topology. If you ever find a gap in your transaction history, you are likely looking at an errant transaction, which occurs when a write happens outside the intended replication stream. These gaps can be notoriously difficult to patch, especially when they diverge across different nodes in a complex, multi-tiered replication group. Solving these discrepancies typically requires purging the offending state or injecting empty transactions to bypass the missing identifiers. I hope this overview clarifies why GTIDs are the standard for production deployments today. Please take some time to review your configuration files to ensure these modes are set correctly for your specific environment. See you in the next session. Welcome back, and let's dive into the mechanics of semi-synchronous replication to ensure your data durability requirements are met. We will focus on the protocol behavior and the configuration variables necessary to protect your transactions from silent data loss. In a standard asynchronous replication setup, the primary server submits a transaction to its binary log and immediately returns a success message to the client, regardless of whether the replica has received the data. This creates a window of vulnerability where a primary crash could lead to a permanent loss of committed transactions if the replica has not yet applied the corresponding events. Semi-synchronous replication introduces a mandatory handshake to close this gap by requiring at least one replica to acknowledge the receipt of the transaction before the primary considers the commit complete. When you enable this feature, the primary thread waits for an acknowledgement from the replica after the events have been written to the replica's relay log. It is important to realize that this mechanism does not guarantee that the transaction has been applied to the replica's data files, only that it has been safely stored in the relay log on the remote side. By enforcing this waiting period, we successfully synchronize the primary commit process with the persistence of data across the network. The primary configuration variable for this mechanism is RPL semi-sync master wait point, which dictates exactly when the primary waits for the replica's acknowledgement. When set to after commit, the primary waits for the replica to acknowledge receipt after the transaction has been committed locally on the primary. This is the default behavior, but it introduces a subtle race condition where a secondary connection could potentially read the committed data before the acknowledgement is received, even if the primary were to crash immediately thereafter. If we instead set this to after sync, the primary waits for the replica to acknowledge receipt before the transaction is actually committed to the InnoDB storage engine on the primary. This ensures that all connections see the transaction at the same time, maintaining a stricter consistency guarantee across the cluster. While aftersync prevents the possibility of a discrepancy where a transaction is committed locally but lost on the primary crash, it does introduce a slight latency penalty because the primary engine must pause while waiting for the network round trip. Managing the health of these connections requires careful attention to their RPL semi-sync master timeout threshold, which defines how long the primary will wait for an acknowledgement before timing out. If the replica becomes unreachable, or the network latency spikes beyond this duration, the primary will automatically fall back to standard asynchronous replication to keep the system operational. This fallback mechanism ensures that your application is not blocked indefinitely due to a network partition, but you must be aware that you are effectively operating without the desired durability guarantee during this period. Once the replica catches up and reestablishes the connection, the primary will automatically switch back to semi-synchronous mode without requiring a server restart. You should monitor these transitions closely because an excessive number of fallbacks suggests that either your timeout threshold is too aggressive or your network infrastructure is experiencing significant instability. Relying on this automated recovery is convenient, but it requires you to be hyper-aware of your replication lag and the actual state of your consistency guarantees at any given moment. To gain operational visibility into this replication topology, you should query the performance schema or the global status variables specifically designed for this purpose. The variable RPL semi-sync master status will tell you whether the primary is currently operating in semi-sync mode or has reverted to asynchronous mode due to a timeout. Furthermore, you can track the RPAL semi-sync master wait sessions variable to see how many client threads are currently waiting for a replica to acknowledge their transactions. Monitoring these metrics allows you to establish a baseline for your expected performance and identifies potential bottlenecks in the handshake process. If you notice a high contention rate in the wait sessions, it is often an indicator that your replica capacity or network bandwidth is insufficient for the volume of writes being generated. Integrating these checks into your existing monitoring dashboard ensures that you receive alerts before a failure state impacts your system's RPO. See you in the next lecture. Welcome to our discussion on InnoDB cluster architecture, where we will examine the high availability stack that powers modern MySQL deployments. When we talk about high availability in MySQL, we are essentially assembling a cohesive stack composed of three primary pillars: MySQL shell, MySQL router, and group replication. You should think of MySQL shell as the administrative interface that orchestrates the entire cluster lifecycle, providing the DBA scripting object that abstracts the complexity of cluster initialization and node management. MySQL router acts as the traffic cop, seamlessly routing your application connections to the appropriate database node without requiring complex modifications to the client-side code. Underlying these components is group replication, which enables the actual data consistency and high availability by allowing multiple server instances to act as a single logical unit. While individual components are powerful, their true value emerges only when they interact in a tightly coordinated fashion to maintain service availability during hardware failures or planned maintenance tasks. This stack is designed to automate processes that previously required significant manual intervention from a database administrator, such as member election and automated failover. By understanding how these disparate parts integrate, you gain the ability to build resilient architectures that satisfy the rigorous demands of production-grade systems. At the heart of this architecture lies group replication, which facilitates state machine replication among a group of independent MySQL instances. We must distinguish between single primary and multi-primary modes, because the choice significantly impacts how your application writes data to the cluster. In single primary mode, only one node in the group is designated to accept write operations, while other nodes function as read-only replicas to guarantee strict consistency. Conversely, multi-primary mode allows any node in the group to process write transactions, which sounds ideal for horizontal scalability, but necessitates a robust mechanism to handle write conflict. Every node in the group must reach consensus before a transaction is committed, utilizing the Group Communication System, or GCS, to exchange messages efficiently. This system is built upon the Paxos Consensus Protocol, which ensures that even if individual messages are lost or nodes experience latency, the cluster maintains a consistent and ordered view of all transactions. Paxos effectively prevents scenarios where different nodes disagree on the sequence of operations, providing the data integrity that is fundamental to reliable database clustering. Deploying an InnoDB cluster from scratch typically starts with the MySQL shell because it simplifies the complex configuration required for group replication across multiple distributed nodes. When you use the dba.create cluster command, the shell automatically configures the necessary server parameters and joins the instance into a new replicate group. You do not need to manually configure every single replication-related variable, as the shell manages both the infrastructure metadata and the internal cluster topology on your behalf. This metadata is stored in a dedicated schema within the database, permitting the cluster to track the identity and state of all participating nodes throughout their operational lifespan. Once the initial node is ready, you use the cluster.addInstance command to integrate additional servers, which the system then synchronizes to ensure they reflect the current primary state. If a node fails, the GCS detects the absence of heartbeats, triggering the group membership reconfiguration and ensuring that the remaining nodes continue to function. Monitoring the health of your cluster is a routine yet critical task that is best handled through the cluster status method available in the MySQL shell. This command provides a comprehensive view of the group health, including the current primary node, the status of every member, and whether any nodes are lagging or unresponsive. By periodically checking the status, you can discern subtle performance issues or network partitions before they escalate into service outages that impact your users. The metadata maintained by the cluster object serves as the definitive source of truth regarding the cluster's health, allowing for accurate automated failover decisions. You should focus on observing the configuration version and the consistency state defined by the GCS, as these metrics are vital for assessing overall system reliability. As you progress, you will realize that the internal complexity of managing Paxos consensus and message ordering is largely abstracted away by this design, leaving you with a robust system that demands consistent oversight rather than constant manual patching. We have established the conceptual framework that makes InnoDB cluster a viable solution for complex data environments. We'll see you in our upcoming session. Hello, and welcome to this deep dive into the internal mechanics of group replication in MySQL 8.0. In this session, we will explore the precise mechanisms that allow a cluster of servers to maintain consistency without a single point of failure. Group replication relies on a distributed state machine approach where every member must agree on the order and validity of transactions before they are committed. When a transaction originates on a member, it must undergo a certification process to ensure that it does not conflict with concurrent updates occurring on other nodes. The mechanism uses a conflict detection algorithm that compares the write sets of incoming transactions against the set of keys that have already been modified by concurrent operations. If the certification process determines that a transaction can be safely applied without violating consistency, it is integrated into the local database state. However, if a conflict is detected, the transaction must be rolled back on the originating member to preserve data integrity across the entire group. This approach effectively shifts the burden of coordination from a central primary to the group as a whole. Because all members see the same sequence of transactions, the replication process remains inherently consistent even under high levels of concurrency. The order of these transactions is guaranteed by a group communication system that acts as the backbone for message delivery. This design is what ultimately allows you to trade potential latency for the high availability and resilience required by modern, mission-critical applications. Managing memberships in such a dynamic environment requires a robust understanding of quorum and view changes. The group maintains a concept of a view, which is essentially the current, agreed-upon list of active members who are participating in the replication process. Whenever a node joins or leaves the group, a new view is generated, and all members must acknowledge this change to maintain stability. This process is governed by the majority rule, which mandates that a transaction can only be committed if it is acknowledged by a quorum of reachable members. A quorum is typically defined as a majority of the nodes configured in the group. If a network partition occurs, the group automatically detects the split-brain scenario by evaluating which side contains a majority of the members. The side that fails to maintain a quorum will automatically cease accepting write operations to prevent divergent data states. This behavior is crucial for ensuring that your database cluster remains a single source of truth, even when network connectivity becomes unreliable. By enforcing strict majority requirements, you effectively eliminate the possibility of multiple partitions continuing to process independent and conflicting transactions.